Good morning, Year 13s. Thanks for coming, guys. I don't know whether or not anyone's on the chat yet. So, okay, guys, I'm very aware that you've got your paper 4 unseen material tomorrow, I believe. So I thought I'd go through the January paper 4 2021 that you guys were had posted on your Google Classroom. So I'm going to spin through it, guys. We know that these papers are long. I'll do my very best to get through it as quick as possible. So let's crack on, guys. Let's crack on. Hide. I'll switch my clip cam on because it makes more sense for me to do that. Hello. Right. Let's get rid of my keyboard. Okay. So, guys, this is the Jan. Let's get rid of that. This is the Jan 2014 paper. There we go. Sorry. Jan 2021 paper, Unit 4. We know that the A2 papers are always tough, so bear with me. I'm doing this paper just like you are, so it'll be interesting to see how I get on and make any amendments on the mark schemes. We know that A2 is always tough. No matter how much your experience is, they're always challenging, and they always do stupid stuff, A2 especially, so we'll bear that in mind. Let's crack on, guys. Okay. Right, so switch to draw. So my name, Mr. Duncan. Me and just reminding you, please don't forget to write your name on the papers. Anyway, right, okay. Got my calculator on standby. Okay, which of these has the highest standard molar entropy at 298 and 1 atmosphere? So I'm looking for a gas. We know that gases have high entropy values. They've got lots of chaos and disorder. So the two gases, carbon dioxide, copper, ethanol, hydrogen, the two that are going to be possibilities are going to be these two. But out of those two, that carbon dioxide, both of them are gases at room temperature, but carbon dioxide is more complicated, being made of carbon and 2 oxygens rather than hydrogen only being a pair of 2 of the same atoms. So I'm going to go for carbon dioxide. I'm going to switch over to red for my mark, for my answers. Reasonable start. The one with the lowest entropy is going to be copper, being the fact that it's a solid at room temperature. Nice to mention it. Okay, the entropy change of the surroundings, and the entropy change of the system for 4 different reactions are given. Which of these is thermodynamically feasible? Okay, so we know that feasibility in terms of entropy is the idea. For something to be feasible, the total entropy must be positive. So the equation I'm using here is the delta S total is going to equal the sum of the delta S surroundings plus the delta S of the system. I've written that backwards, doesn't make any difference in this case. But we need this to be positive. So P is definitely positive. The reason being is both values are positive, so no matter how the equation's done, it's always going to give me a positive total. So that one is possible. The next one is the entropy of the surroundings is very positive, plus 350, but the entropy of the system is minus at 276. Now, in this case, it doesn't make any difference because we're adding the two together. Because there is a more positive value, the entropy total will still end up being positive. So Q is also possible. The next one is we have a huge negative surroundings with a small positive system. That's not going to be possible. And then S, God no, that's never going to be feasible. Done. Okay, so the answer is P and Q. Next. Which equation represents the standard enthalpy change for the atomization of bromine? So the standard enthalpy change of atomization is the heat energy change when 1 mole of atoms is formed from its constituent elements in their standard states and under standard conditions. Now, the standard state there from the element bromine is going to be a liquid, and we need to form 1 mole of bromine gaseous atoms. So the two that we're always going to be iffy about is A and C, because we've got half a mole of bromine liquid going to 1 mole of bromine gas. That there is atomization in regards to bromine element. Yeah. So, and the other one is going from gaseous, so it's out of its standard state. Yeah. Now, what's interesting there is when you run atomization of compounds, they need to be gaseous. No, that's bond dissociation. You can't break a bond without it being a gas. So, but because it's enthalpy of atomization of bromine, we need to make sure it's in its standard state. So I'm going to go for A. That's tricky, that first one of interest. It could be C. Could be C. The question is about ionic compounds. Which of these compounds would be expected to have the least exothermic lattice energy? So this is which one is going to have the weak. We know that if you take an ionic compound, yeah, and these two come together, they're making a bond. It's going to be exothermic, and it's going to give out energy. Well, what we need to have is, to have the least exothermic, we need the weakest bonds. Yeah, so calcium chloride is made of Ca2 plus and Cl1 minus. Yeah, this is Mg2 plus. I've switched over my things there. I should really stick with the same thing. 2 plus and 1 minus. This is Cl1 minus. This is K plus and Cl minus. Yeah, and then Na plus and Cl minus. I'm just going to switch to doing the minus, hit the 1. Now, we want the least exothermic. So we want the one to be the weakest attraction. So that immediately eliminates both calcium chloride and magnesium chloride. And it's now between these two. Now, the chloride ions are the same size, but potassium is larger than the sodium. So what that means is that the sodium is going to form stronger bonds because it's smaller. So C is going to be the least exothermic, producing the weakest attraction between them. The stronger the attraction that's being made, the stronger the bond, the more exothermic. So the least exothermic would be the weakest bonds. Which of these compounds would be expected to have the largest difference between the Born-Haber and the theoretical lattice? So this is the PIM model, the perfect ionic model. Perfect ionic model states perfect spherical ions and only electrostatic attractions. But the Born-Haber cycle takes into account that the cation can distort an anion. So what that means is that there's always a slightly higher Born-Haber than there is lattice energy. Now, which one's going to be the most polarizing? We can immediately eliminate the potassium, sodium, bromide. We've drawn the pictures, yeah, because the calcium is a 2 plus, and it's going to distort the anion more. Notice that. Oh, but then we've got a bromide ion in there. But the potassium, oh, yeah, no. Okay, so the answer is going to be A. And the reason being is, remember that the size of the anion does make a difference. It means that it's more easily polarizable. But then these are all only +1 values. Yeah, the two that would be umming and ahhing here really would be sodium bromide and calcium chloride. But I know that the calcium 2 plus ion is going to be a lot more of an impact on this one. And I know that calcium chloride's also got a strange. Hi, Nikita. Nice to see you. Thanks for coming, Nikita. If you've got any questions, Nikita, please just give me a shout and I'll go through any questions again. Give a bit more detail if needed. So calcium chloride there is going to be, because it's also got a distinct difference in its melting point. All the group 2 chlorides are rather strange due to their polarization. Okay, the standard molar enthalpy change of the solution of potassium chloride is +17. The solubility of the chloride ion is, wow, massive, 359 grams per liter, when it's an endothermic process. That's all it is, which will explain it. It's going to be entropy. Yeah, the total entropy change when KCl dissolves is positive. It's going to be C. Yeah, so just to point out, the hydration of K plus and the lattice energy are well, the hydration of that is correct. The lattice energy are both exothermic. Yeah, that's true. Yeah, but B is complete garbage. Why would it not talk about the hydration of the chloride ion? That is also exothermic. Very odd. But anyway, for something to be happening, this here is endothermic, which means it shouldn't happen. But we know that if an endothermic process is happening, it's because the entropy of the entropy change, the total entropy change is going to be very positive, which will overcome it. Yeah, technically that comes down to Gibbs free energy, I believe. Yeah, delta G equals delta H minus T delta S. And if, or you could also simplify it down to delta H equals T delta S. And what you realize is that the delta S is outweighing the enthalpy change, the small endothermic, and driving the reaction. Next, the total entropy change is this. The value of the equilibrium constant for the reaction would be, okay, so this is shrink, yeah. So delta S total equals R ln K. So I teach this as shrink. I know that it's not. Challenge Flex. I love watching your videos. They help a lot. Challenge, you're very welcome. I'm glad they help. So I just teach this as shrink. I know that it's not at RLNK. I know that RLNK. I know that it doesn't spell shrink. You could say shrink if you like, but I say shrink because it's easy, and I just remember that the S doesn't really exist. It's the only way I can really remember this equation. It's nightmare, this. And so that's how I do it. So what they're asking me to do is to calculate an equilibrium constant, which is K. So I need to reorganize. So the delta S total over R will give me ln K. Let's reorganize that. So now it's given me the total entropy change there. So now I can say minus 85 over the equilibrium constant, of course, which is just, over R, which is 8.31, is going to give me ln K. Let's run that through my calculator. Minus 85 divided by 8.31, which gives me minus 10.2 equals ln K. Now I need to get rid of the ln. I need to E both sides. So the opposite of ln is E. So I'm going to go Shift E, answer, which will give me 3.61 times 10 to the 5, which is A. Yeah, so what I've done is I've E'd both sides. So I've E on my calculator and Shift ln, yeah, E minus 10.2 should give me K. And that's what I've done, which then spat out that number. Yeah, know your calculator, folks. So it seems reasonable to me. Let's go for that. Okay, propanone reacts with iodine in the presence of a catalyst of dilute hydrochloric acid. The reaction occurs in this equation. The rate equation is this. Okay, so they've given us the rate equation, and it's telling us that this is first order. Yeah, this is first order. Shouldn't do that since it's primary. That's first, and this is first. So what we now need is we need the slow step to contain both of these people. That's what we need. So the first thing I'm going to do is I'm going to skim them. So this one is the fast step. There's H plus, and there's our propanone. Oh, see what they've done. The answer is A. I'll come back to that in a minute. I'll explain why in a second. And I go, it's fast. I'll skip it. The next one is that I have these two and these two again, which are in the step here, but that's still fast, not that one either. Then I've got propanone, but H plus is a product, and that's slow. That's definitely not the right one. And then this one, once again, no H pluses, even though it does have HI, which is an acid itself, but there's no H plus in the equation, so I'm not going to say it's D. Now, what that means is I've essentially now eliminated all four answers, which is incorrect. And now I realize that it's A. Now, this is really sneaky, guys. And the reason why it's A is because the slow step here is actually only made up of this guy, which is the product of the first fast step. What that means is that this guy here is a combination of both of these two. And since there's no other reactant here, since there's no other reactant at this point here, it means that the only people in the slow step must be those. So the answer's A. That's really hard Don't like that one bit. Grim. Next. Okay. The rate equation for the reaction is this. Why have they bothered to show that? They're just trying to piss you off. Yeah, the initial rate of the reaction is this with an 0 point. What is the value of the rate constant? Right, so just make B vanish. Yeah, let's reorganize for the rate constant. So that's going to be rate equals rate over A squared is going to give me K. Well, let's just insert B I don't give a crap about. Sorry, excuse my French, do apologize. It's the first time I've done that. A is 0.3, and there's my rate. Insert my numbers. 9 times 10 to the 9 minus 5 divided by 0.3 squared will give me K. Got to be careful of my units. The units are just, what is the value of the rate constant? Okay, that's fine. Cool, so my units are exactly what they've given us. Those are correct. So 9 exponential minus 5 divided by 0.3 squared, and I get a value of 1 times 10 to the minus 3. I'm going to go for C. Okay, that's 1 times 10 to the minus 3, and there's my answer. Next, this question is about weak acids. pKa of ethanoic acid is 4.8. pKa of chloroethanoic acid is smaller. What is the pH of a solution of chloroethanoic acid at this point? Okay, so this is just the pH of a weak acid. So what that means is, because this is, by the way, this is multiple choice, we can do this relatively briskly. So the equation, because it's simply a weak acid, I'm actually going to do this properly. Yeah, and that would then be CH2ClCOO minus all over CH2ClCOOH. But we know that this is a weak acid. So these two here are the same. So I can simplify that now down to H plus squared. Now what I can do is I can reorganize my equation, bring that over to here. Yeah. So at that point, I'm going to multiply both sides. So multiply both sides by the concentration of the acid, which is that. So that's 0.1. So that one's dropped over to here. That is 0.1 molar from the equation, just moving it over. So that now vanishes. Then I'm going to need to root it, yeah, to get rid of the squared value. Now, of course, I haven't been given Ka. I've been given pKa. So I've got to flip that out. So that's 10 to the minus 2.5, because the opposite of pKa is that. Yeah, we've got to anti-log this. So I'm going to do, if anybody's interested why it's minus, pH equals minus log H plus concentration. Well, if you wanted to get to the opposite of that, you've got to move everything over. Yeah, I hope that makes sense. Yeah, because it's a negative. So first thing is, if you flip it, let's flip the thing and go to that. So that becomes minus, that becomes a plus. Yeah, so minus the pH equals that. That gets rid of the minus sign. Now to get rid of the log is the opposite. So I need to everett. So I need to anti-log it, which is 10 to the minus pH equals H plus. Just explaining that a little bit, guys, just to give you a bit of a base on that bit. So I'm going to do shift anti-log minus 2.9. That gives me a Ka value of 1.25. That gives me a Ka of 1.25. Oh, 2.6 technically. 2.6 times 10 to the minus 3. That's quite a strong acid. It's quite a strong weak acid. So I'm now going to do root 0.1 multiplied by my Ka value, which is there on my calculator, equals, and I get a pH. I get a H plus constant. Oh, absolutely, that's interesting. I've just got, what is the pH solution? Oh, what is the pH of this? Okay. I've just worked out a H plus concentration. So my H plus concentration, is 3.98 times 10 to the minus 4. Right now I need to minus log it, minus log answer. That seemed awfully long, 3.4. Oh, and I haven't got any of those answers. Oh, that's interesting. What have I gone and done? Chloroethanoic acid. Let's anti-log that again. So anti-log to get to the Ka value. So shift anti-log minus 2.9. 1.25 times 10 to the minus 3. Fine, there's my Ka value. There's Ka. Yeah. And the concentration of the ethanoic acid is this. So that does drop in here. Multiplied by the, so let's multiply that by 0.1. Takes that root answer. Maybe I've done it answer. I've changed my answer. Yeah, root answer to give me the H plus, which is 0.0. My calculator error. Calculator error. Now minus log answer, and I get a pH of 1.95. B. Thank you very much. So what I just did there, folks, is I did that bit first, and then I rooted my answer, just so you know. It was a calculator mistake. I don't know what my calculator was doing, but it didn't like it, whatever I did. So it's fine. All came out in the wash eventually. B. Next. Which is the acid conjugate base pair in the reaction of ethanoic acid? Okay, so just to let you know, so we've got chloroethanoic acid reacting with ethanoic acid. Now, anybody here who knows the acid-base theory, what you realize is that this one here is stronger than this one. Yeah? So, and just to explain why, the reason being is that the chlorine group is highly electronegative. Yeah? The chlorine group is going to suck electron density towards it. So the electrons in this molecule are going to get sucked towards her. Now, what that means is that this bond here is going to become more polar. So in ethanoic acid, there's no chlorine dragging it. So here's the difference. This is now delta plus and delta minus, and this one is delta minus and delta plus. It's less polar. That's less polar. What that means is fewer of them will break away. So if fewer of them break away, then this is a weaker acid in comparison to this one. This one's a stronger acid than that one. Yeah, I'll put both as weak acids, but this one's stronger. So what that means is this one's going to protonate this guy. Yeah? So what it's actually going to do is it's actually going to protonate it up here. That's where it gets transferred to, just so you know. Yeah? So what's going to happen is I'm now going to form CH2Cl, COO minus, plus CH3COOH2 plus. So the conjugate, the acid, is him, which is either C or D, and then the conjugate base is going to be its salt, which is that guy. They're the conjugate acid-base pair. I hope that helps. Okay, next, acid-base titration curves. Titration curves, which region of the graph represents the most effective buffer region? That's U. By the way, not a particularly good buffer region. That's interesting. Not a particularly good one because it's not exactly level, is it? But it's still a buffer region. We know these regions now. Yeah. Which of these is the best indicator? Use the data booklet. So I downloaded the data booklet a while ago. I keep it on my desktop. So what I now need to do is find... The great thing is I'm so glad they changed the data book because it's tiny in comparison. Look for my indicators. Indicators, there are my indicators. Right, so I want an indicator that's going to change color in the vertical region. So that is between vertical region, there and there. So that's 1, 2, 3 to 6.5, give or take. Yeah, I'll say 6.5. Between 3 and 6.5 is where I need it to change. So I'm simply looking for one. So methyl orange seems valid. 3 to 6.5 seems reasonable. So methyl orange, possible. So number 3. Are there any others that are in that? Bromo crescel green also would work. PK and, yeah, I don't really care about those. So, okay, let's label them. So methyl orange is changing 3.2 to 4.4. So that's going like right there. 3.2. Yeah, I think that's reasonable. Only just though, but yes. The next one is 4.6 as we're coming down. That would 4.6. The next one, it's got very large range there. The bromophenol blue is going to change at 4.6 to 2.8. That one will work. Don't see why we wouldn't choose that one. 3.8 to 5.2 for bromocressyl green. 5.4 to 3.8. Seems dead in the middle. Next one, methyl red to 6.3. That would only just litmus. No, they're all too high. So we're definitely in this region. Now, of all of those indicators there, which one would I choose? I'd probably go for the one that's right in the middle. I'd probably go for the bromocressyl green. Seems right in the middle of the indicator region, in the vertical region. So what options do I have? Methyl red. Oh, it's choosing them for me. Methyl red, phenol red, phenolphthalein, and thymol blue. Huh. Okay, so that's hilarious. I did all that work for no reason. Let's now use the ones that they've given me. So, methyl red, 4.2. 4.2 to, was this methyl red? Yeah, 4.2 to 6.3. So it's going to go at 6.3, which is right there. Blimmin' methyl red, 4.2. And then I've got phenol, sorry, that's methyl red. Then I've got phenol red, which is 6.8. That's going to go too early. That's phenol red. Phenol, that's going to go too early. And then phenolphthalein, way too early. That's up here, phenolphthalein. And then thymol blue is 1.8. That's way too low. So it's either between methyl red and phenol red. I'm going to go for methyl red. Going for that one. Seems reasonable. It's within the vertical, and that's what I'm going for, guys. Next, I'm going to switch that back out of pink and into red. There we go. That's what I'd go for. Next, what is the approximate pH of ammonium chloride? Right, ammonia is pH 11. You need to know that one. It's pH 11. Now, ammonium chloride is its conjugate base. Yeah, this is that's a base, and this is its conjugate acid. So it's going to be slightly acidic. pH 11, it's going to be slightly acidic. It's not going to be 2. It's not. These are all basic, so the answer is B, 5.8. It's slightly acidic. Next, a diprotic acid was titrated with sodium hydroxide. Oh, nice bog standard titration question from GCSE. It's quite nice. So a 25 centimeters cubed, 0.1 molar. I've done that. Sorry, I've done that for sodium hydroxide. And I'm now titrating it with 12.8 centimeters cubed of my diprotic acid. Yeah, complete for the, what is the concentration of the diprotic acid? Okay, so the moles are going to be the same. So we need to work out moles of sodium hydroxide. So that just becomes C, calculate one, C times V over 1,000. That gives me 2.5 times 10 to the minus 3, because I simply just used this equation, of course, just to reiterate what I was doing. Sasha, hi sir, I have my unit 2 again tomorrow. Do you have any tips? Good luck. Yeah, practice your energetics today. Make sure you've practiced calorimetry. Make sure you've practiced your Hess cycles or ability to ignore Hess cycles. Have a look at energetics. Yeah, definitely. Have a look at some past papers on energetics. Just make sure, because Q equals MC delta T is going to be there. Yeah, there's probably going to be a horrible graph. Do the best you can, Sasha. You're going to do great. I hope all my videos have helped. Right, so we know that number, it's a 2-to-1 ratio. So those moles are going to be divided by 2, which gives me 1.25 times 10 to the minus 3. Right, so now I've got a volume and I've got the moles. I can just reorganize this. So moles is 1.25 times 10 to the minus 3 times 1,000, bring 1,000 over the volume of 12.8. Gives me 1.25 divided times 1,000 divided by 12.8. Boom, 0.09 Eng, 9.7 times 10 to the minus 2. Okie dokie. So it's that one. B. Moving on. A sample of bromoalkane, RBr, containing a single optical isomer reacts with hydroxide ions in an SN1. The alcohol formed is racemic. What can be deduced? It's tertiary. So just to tell you, the SN1 there is the trick. Yeah, and also the fact that it becomes racemic also tells you. So SN1 reactions, yeah, these are tertiaries. What happens is a tertiary haloalkane goes through an initial step where it splits apart to form these guys. Yeah, and then this is now SN1 because that step there is, this step here is fast. Yeah, but this step here is slow. And there's only one species in it, hence SN1. One species in the rate determining step, and tertiaries are what go through this. Yeah, so tertiary it is. If it, yeah, I'm just gonna leave it there. Next, a compound X has a molecular formula. It gave an orange precipitate with 2,4-DMP, C double bond O is present, and gave a silver mirror with toluenes, aldehyde. Yeah, there we go. So which one could not be X? That's an aldehyde, that's an aldehyde, that's an aldehyde, that's a ketone. No, that was easy. Wow, fast for once. Propylethanoate is hydrolyzed with aqueous sodium hydroxide. What is formed? So this is an ester. Yeah. So we've got this structure here, and then 3, 1, 2, 3. So this is the alcohol section. Here's the ol, and here is the oic. So if I hydrolyze this with sodium hydroxide, the oic is going to become the ethanoate ion. Yeah. And the other guy is going to become the alcohol, propan-1-ol. Yeah, that's what it's going to become. Let's track them down. C. Lots of C's. No, okay, maybe not. 2.95 grams of ethanoic acid is produced from ethanol. What is the percentage yield of ethanoic acid? Okay, so we take ethanoic acid. Oh, produced from ethanol. So irritating. So oxidation. Yeah, plus oxidizing agent goes to ethanoic acid. Yeah, and water, by the way. Balance the equation, I believe. Yeah, I think that works. It's a 1-to-1 between the ol and the oic. So what we need to say is, well, if we've got produced from 2.5 grams of that guy, how much would I have done? Well, moles is 1-to-1, so I've just got to get that to moles. Grams over rams. Divided by 46, they've given us the MR. Yeah, so 2.5 divided by 46 gives me 0.0543. So 1-to-1, 0.0543. Multiply that by 60. How much should I get? Multiply it by 60. Gives me 3.2 grams. I should have made 3.26 grams. Okay, how much did I get? Well, I got 2.95. So 2.95 divided by 3.26 times 100, and I get my percentage yield. So 2.95 divided by answer times 100, and I get 90.5% C. There we go. A mixture of organic compounds was analyzed using thin layer chromatography. The RF value was 0.9. Wow, that's traveled a long way. Guys, they've done thin layer chromatography. The baseline was here, and the dots up here, and the solvent front is there. That's traveled a long way. What that means is it's got a very low affinity for the stationary phase and a high affinity for the mobile phase. Mobile phase is carrying it. Attractions between component and stationary phase are very weak, so it's either him or him. The attraction between the component and the mobile phase is strong. The answer is D. Wow, that's a very high RF value. Next, end of multiple choice. So what's the time? Be quite nice to know the time here.
It's a very high RF value.
Wow, I didn't even realize I was running. But I'll pause that. So that's been running, started 34 minutes ago. So it's taken me 34 minutes to run those multiple choice. It's not great. I've been doing a bit much of the explanation, but still a long time now. Now the total paper is 1 hour 45. So I've got 1 hour and 15 left to go, give or take. Okay, so let's crack on. Okay, this question is about carboxylic acids and their derivatives. Lactic acid is produced in muscles as a result of anaerobic respiration. The structure of lactic acid is this. Give a reason why it shows optical isomerism. The carbon is chiral. Lactic acid molecules have a chiral carbon. You could also say produces two non-superimposable mirror images. You could have said that the carbon contains 4 different groups, so it is chiral. I'm pretty sure that'll be enough. Lactic acid molecule has a chiral carbon. 4 different groups attached. I'll just leave it there for 1 mark. Leave it there. I'm going to get rid of my thing there so I can see my chat. Hi, Mr. Duncan, revising maths right now. We'll watch this after the exam. No problem, Winkit. A laboratory sample of lactic acid does not rotate the plane of polarized monochromatic light. Give a reason. It's racemic. The sample is a racemic mixture, so no overall rotation. Give the structure of the organic product when lactic acid reacts with concentrated phosphoric acid. Right, concentrated phosphoric acid, that's a dehydrating agent, similar to sulfuric. It's going to react, by the way, the acid wouldn't react with the acid, would it? What's going to happen is it's going to dehydrate it. It's going to remove the old group and create an ene. So let's draw what lactic acid actually looks like, because I think that's probably quite useful. Yeah, and I think, yeah, the old group is on the middle carbon. So it looks like this, stick. Right, now concentrated sulfuric acid is used for converting an alcohol into an alkene. Now what that means is I'm going to remove him and him to make water, dehydrating, and the double bond's going to drop in here. It can't drop onto the other side because of the OIC group. Yeah, it can't drop onto the other side. So give the structure. So I'm now just going to make that vanish. There you go. This one. Lol. Next. Okay. Identify X. So we've got butanoic acid. We've done acidified potassium dichromate under reflux. We started life as an alcohol. Yeah, and it was a primary to boot. So the identity of the alcohol is butan-1-ol. Identified by name or formula. Okay, so it allows us to do everything, and it's big, we can draw it. I'll draw it, they've given me the space, I'm drawing it. It's going to be butan-1-ol. It's under reflux. If it had been under distillation, we could have actually thought it might have been the aldehyde, butanol, but in this case, it's definitely butan-1-ol. Reagent Y, so we're now going to convert the carboxylic acid into an acyl chloride, PCl5. Name or formula, PCl5. Compound Z. Right, we've now taken the acyl chloride and reacted it with an amine to form an N-substituted amide. And it's allowing me to draw that too. So this is what it started life as. It started life as the acyl chloride, and the amine has hopped on. Now, the amine that I had was methylamine, yeah, which makes everything a little bit easier, to be fair. Methylamine, this is methylamine. And what happens is, of course, it's going to go through nucleophilic addition elimination, yeah, and it's going to attack that carbon because it's polar around this bond. That hops up there. Yeah, I'm actually doing the acyl chloride mechanism here. I won't bother with the whole thing. But anyway, the point being is, in the second step, the chlorine hops off. Yeah, so I'm now going to attach that. I ought to do that all properly, really, and show you that mechanism in its entirety, but I am worried about the time. So I've now attached on this N with its little group. Yeah, I've now formed an N-substituted amide. That is N-methyl butanamide. There we go. Get rid of my polarities, not needed since it's not a mechanism. Next. Okay, polyesters, just cutting the ester linkage. Give the structure of the two monomers. So we've got ethane 1,2-diol. That was nice and easy. Very common. Ethane 1,2-diol. Yeah, and then we've got a very odd dicarboxylic acid with a C double bond C in it. That's very strange. Now it's also, they're going up and down, which means I need to stick to it being up and down as well. There you go. It's very interesting. It's a diene. So that would be but-2-ene adiene. Well, yeah, enadiene. That's horrible. Grim. Don't ask me about that. Yeah. Okay. An organic compound E contains carbon, hydrogen, and oxygen only. The accurate relative atomic masses of the elements of these. E contains 5 carbon atoms and gives a molecular ion peak at 102.0678. Deduce the formula. Okay. 5 carbons. Let's just keep it simple. 5 carbons. I've got hydrogen. So, okay. So, the options we've got here, it doesn't even give us a molecular formula. Oh, that's kind of the point. Okay. So, what we can now do is we know we've got 5 carbons, C5. So, that's going to be 12 times 5. 12 times 5 gives me 60.00000. Yeah. What have I got left? I've got 102.0678 minus 60. So 102.0678 minus 60 gives me 42.0678. Right. 42, that's not a huge amount. So if I have, let's just consider the oxygens, because the problem is there's going to be loads of hydrogens, but the oxygens are really big. So I could have 2 oxygens here. It could be an O2. Well, if I had an O2, yeah, that would give me 15.9949 times 2. Yeah, that would give me 31.9898. Right, and then how many oxygens would I have left? So this might be O2. H's, how many H's would I then have? Well, if I put on an O2 on any of these, yeah, it could be an alcohol. I don't have many left. That was it. So the difference therefore is 10. So that'd be, 42. 42 left. Minus, so I'm now going to minus 31.9898. 42.0678 minus 31.9898 gives me 10.078. 10.078. For 1 mark, this sucks. 42. Let's simplify this, folks. There can't be that many versions of this. C5, H, X, O, Y. And that needs to add up to 102.0678. Right. So straight away minus 60. So take away that. So minus 60.0. Let's just do that bit and go 102.0678. This is grim. Minus 60. Okay, so HXOY equals 42.0678. Right. So, we can do it algebraically. It sucks, this. Really sucks. I don't like it. Can't be that many. So, well, we've got to have the maximum number of H's we can have is 12. H's max out at 12. 12 H's max. Yeah. 12 H's, let's just test it. 12 H's. And I need to hit this number. 12 H's plus 1 oxygen. Yeah, so 1.0078 times 12 plus brackets 15.9949. Well, that's if I add 1, that's only going to be 25, so add 2 of them times 2. 44, that's too big. It's too big by 2, because if I do 2 O's, that gives me 44.0834. Right, so get rid of 2 of those. Let's do 10 H's. 10 H's is 1.0078 times 10 plus, there's the 78. Just picked up the 78 there. Plus brackets 15.9949 times 2. That's really grim, that. Fortunately, but there's my answer. That's horrible. C5H10O2. Guys, horrible question. And do you know what? For 1 mark, I would honestly ditch that question in an exam. If I was doing this paper under exam timings, I'd just go, can't be asked. I'd just bail on it. No way would I be bothered with that. Not worth the time. It's taking me like 5 minutes to work out a 1 marker. Nah, bail. Aqueous sodium hydrogen carbonate is added to a sample of E. No effervescence occurs. So it's not a carboxylic acid. Not a carboxylic acid. Yeah, that's the test for a carboxylic acid. The infrared spectrum of E has an absorption in the range of, name the functional group. Data sheet. Absorbances. Infrared, please. Give me my infrared. There. And they've given me a specific value, you see. 1750 to 1735. 1750 to 1735. There. Ester, saturated. It's an ester. Gave us a very distinct region. Next. Data from a high resolution gives me this. Okay, deduce the structure. So good old NMR puzzle. Right, first of all, look for all the pairs. Holy moly. Got a sextet in there. It's a sexy chemistry. Sextet chemistry. Right, so we've got a sextet, a CH2, which is a sextet. That means it's got 5 carbons next door, 5 hydrogens next door. This makes total sense with the other splitting patterns. It's got to be that. Can't be anything else. Yeah, so I've got that structure there immediately just from him. Now this guy here, and label them. This guy here is going to be a CH3 group, but a triplet because of the next door. So that one there, this one here is D. D. This one here is going to be C. This one here must therefore, because we've got another, because I know that must be C, because it's the only one with a 2, which is a sextet. So I've ticked off these guys. Yeah. Now I've got a triplet 2 again, which is him. That there must be A. Yeah, which means it's also mustn't have any other hydrogens next door. We've got one person missing, which is B as a singlet, which is CH3, because it's got an integration relative peak area of 3. Right, and it's an ester. We know it's an ester. So the question, so I can label him now, that one's going to be B. So we've got everything we need to build this. Whoops, B. And now we just need to link it together. And in order to get the ester linkage the right way round, we need to look at the shift, because that triplet there, B, yeah, that B here has a shift of 2.5, whereas A has a shift of 4.2. So it'll flip over the ester group, the ester linkage. So what we need to do is we need to go to our NMR, and we need to go, okay, so ester, right. So the ester on the O, which is this guy here, if you can see my mouse, might not be able to, is high on the O, is in the 4 region. So ester on the O is high, and the triplet is high. So it is that way round. Done. Horrible question. NMR, gains, it's all gains. Next. A catalyst of vanadium 5 oxide is used in this reaction. State the effect of any on the value of Kp. No effect. The only thing that affects that Kc and Kp is temperature. No effect. No change. The temperature used for the reaction is 700 degrees in industry. Explain in terms of equilibrium constant on the equilibrium position the effect of increasing the temperature on the equilibrium yield. Okay, 2 marks, don't overthink this in terms of equilibrium constant. Okay, so what happens to the equilibrium constant? The first thing is bullet point number 1, forward reaction. Forward reaction is exothermic. Knowledge reaction is, this is technically COFC, by the way. COFC. Knowledge, oppose, favor, shift, yield. Forward reaction is exothermic. Gotta say that. Can't really avoid it, even though it's only 2 marks. So what's going to happen in terms of the, so if I raise the temperature, increasing the temp, it's going to favor the endo, it's going to go backwards. So the equilibrium is going to shift from right to left, and the yield will drop. If there's less yield, there's a lower Kc. Kc will decrease as temp increases. I'm going to write temp, you're not allowed to do that in your exam. Yeah, the yield will also drop. Yield will also decrease. Done. That'll do. Write the equation for the equilibrium constant Kp and state it. So this is sulfur dioxide to sulfur trioxide. Kp equals products over reactants. SO3, close brackets. Remember, they're not square brackets. You're not allowed to do that. And this is a partial pressure over the partial pressure of SO2 to the power of 2 and the partial, multiplied by the partial pressure of O2. And I think that's to the power of 1, is it not? Yes. All gases, all good. Done. Products over reactants in round brackets because it's pressure, not concentration. A mixture of 0.2 moles sulfur dioxide, 1 mole allowed to reach equilibrium. Yada. Okay, so SO2 plus O2 goes to SO3 in equilibrium, and there's 2 of them. So the start mix was 2 moles of that, 1 mole of that, and none of that. At equilibrium, at equi, I have now got 1.60 moles of him. Right, well, that's a 2 to 2, so that's going to drop by 1.6 and be 0.4. This one is a 1 to 2 ratio, so if this here is 2x, half of it is 0.8. So that's going to decrease to 0.2, and I'm done. Yeah, so because x equals 0.8, yeah, so this one's going to decrease by x, and this one's going to decrease by 2x. I hope you understood what I did there, guys. So now I've got my moles. This is my moles at equilibrium. I now need to work out their partial pressures, their PPs. So their partial pressures are these multiplied by the total pressure, 5 atm, 5 atm, 5 atm. Yeah, okay, working out their partial pressures based on the total, 0.4. Hang on a minute. Do I need to multiply them by the mole fraction first? Don't know. Hard to find out. Yeah, I need to turn them equilibrium moles. I need to work them out into their mole fractions. Yeah, mole fraction first. That's mean. Sorry, I've forgotten my process. Total moles, divide that by the total moles, which is 0.4 plus 0.2 plus 1.6. Gives me 2.2 over 2.2. I need to work out their total mole fractions in the mixture. 0.4 over 2.2. If I don't do that, it won't add up to 5 in the partial pressures total. It won't add up. 0.2 divided by 2.2, 0.0910, and then 1.6 over 2.2 gives me 0.727. Right, those are my mole fractions. Now I can turn them into their partial pressures by timesing them all by 5. Now what that should mean is, when I do this, all of the mole fractions should add together to be 5 atmospheres. That's what should happen. I've got the last one already, so times 5, it's already on my calculator. That's 3.64 ATMs. Yeah, 0.0910 times 5 gives me 0.455. And then 0.182 times by 5 gives me 0.91. And if I add all of those together, it should give me 5. 0.91 plus 0.455 plus 3.64 equals 5.005. That's perfect. So these are my partial pressures, right? Now I can work out Kp. Is 4 marks. Include a value for the thing. So Kp equals partial pressure of SO3 to the power of 2 divided by the partial pressure of SO2 to the power of 2 multiplied by the partial pressure of O2 to the power of 1. So run those in. So SO3 is here, O2 is here, SO2 here, run them in. Kp equals 3.64 to the power of 2 over 0.91 squared times by 0.455. Run that through my calculator. 3.64 squared divided by brackets 0.91 squared times by 0.455, close brackets, gives me a Kp value of 35.16. Now, what we need to realize is it's going to have units. Those units will cancel with those units, and those units will bring up. So this is going to be ATM to the minus 1. There's my answer. Moving on. I don't waste any more time with it. Sulfur trioxide is used to produce sulfuric acid. Commercial concentrated sulfuric acid contains 95% sulfuric acid and 1.5% water by mass. The density of concentrated sulfuric acid is this. Calculate the concentration of sulfuric acid in moles per dm cubed. Ugh, grim. Right, that's gross, that guy. So really what you're doing is going from grams to moles. But the problem is they've thrown in here an additional percentage question. So would everyone agree? Usually, this is a GCSE game. Usually you're just going from grams to moles, which is grams over rounds equals moles, because the dm stayed the same. However, the problem is they've thrown in this percentage. So that mass there isn't entirely sulfuric acid. It's 1.5% of that is water. So first thing I need to do is work out the mass of sulfuric acid in that liter itself. So multiplied by 0.985, which is its percentage. 1800 multiplied by 0.985, go, which gives me 1.773 grams per dm cubed. Sorry, get rid of this last GCSE habit. Grams per dm cubed sulfuric acid. Right, now that I've got the sulfuric acid, I can convert it to moles. So how much does sulfuric acid weigh? 2 plus 32.1 plus 16 times 4. 98.1. Let's just check that. Periodic table. Sulfur, 32.1. Yeah, 98.1, fine. That's 98.1. So divide that by 98.1. So 1.773 divided by 98.1 gives me 0. That's weird. Grams over rams. Yeah. Moles per liter. 0.018 gives me moles. Yeah. moles per liter. Seems awfully low, that. I was expecting it to be really high. This is concentrated sulfuric acid. This doesn't make sense. Grams per liter. Moles per liter. Oh, bloody hell. I've had it in a decimal place. I've had it in a 1. That's 1800, and I was meant to be doing 17. I'm an idiot. 1773 divided by 98.1. I'm an idiot. There you go. I'm an idiot. 18.07 moles per liter. I'm done. Next. The pH of 0.1 molar sulfuric acid solution, alarm bells, diprotic, is 0.97. Calculate the concentration of the hydrogen ions. Okay, so anti-log. They've given us the pH. Yeah, they've given us the pH. So we know that pH equals log, it equals 10 to the minus pH. No, hang on a minute. H plus equals 10 to the minus pH. So just run it through. So 10 pH is minus 9, 0.97. Gives me shift log minus 0.97. That's not right. Damn cubed. Should have been double. Strong acid. It's not sulfurous, it's sulfuric. Question mark. In an aqueous solution of sulfuric acid, the following equilibrium exists. No, it doesn't. Ka very large, fully dissociated in there. Explain in terms of these equals why the concentration of hydrogen ions in 0.1 moles per dm cube solution is not 0.2 moles. It should be. I'm going to email it Excel because that's not correct. I don't believe that. I can do that practically. I call. Okay, just move on, accept it. Explain in terms of these equals the concentration is not. Okay, no calculation is required. First, loss of first, that's really thrown me that. Loss of first proton is complete. Hence the Ka very, very large. Since Ka is very large, seen this kind of question before. I see what they're doing. I call bullshit. It's rubbish. First equation makes, we've seen this before, makes H3O plus, which pushes second equilibrium to the left. So this one generates this. We've seen this question from Edexcel before, and this H3O plus will push the second equation back in the other direction. Yeah, that's why to the left. I'm done. I'm not doing any more on that. It's garbage. A buffer solution is made from, is that even possible? I didn't think that was possible. Write an ionic equation involving H2 and H to show how this solution acts as a buffer. Okay, so HSO4 equilibrium going to SO4 2 minus, there's minus, right. So that's the first one. So the first thing is that this one can lose a proton. Yeah? So if we do the reaction with an acid, so by the way, this is the acid, yes, and this is the conjugate base. So if I add an acid, it'll do this, H plus, and it will drive it back in the other direction. I hate writing equations backwards. And then the other equation will be that OH minus reacts with HSO4 minus, going to form SO4 2 minus plus water. It's just such garbage. Yeah, those are correct. That's horrible, that. It's grim. This is the acid reaction. This is the base reaction. The way I got to them was I wrote down the equation. I wrote down the two people in this buffer. Yeah. And then I said, right, who's going to be the acid? Well, if you actually balance the equation properly, you realize that this guy is the acid because it's losing the proton. Yeah. Therefore, this guy must be the conjugate base. What I then did was split them up. I said, if this is the acid, it's going to react with the base, OH minus, and then I balanced the equation to form the conjugate salt and water. I then said, well, if this guy is the conjugate base, then I'm going to react it with acid, which is H plus, and I'm going to form HSO4 plus. So that's the way I built it, just for future reference. A buffer solution is formed by mixing. Okay, can I just point out, I'm hating this question right now. It's seriously annoying me. So this is the salt. We know that this is the salt. Yeah, and this is the acid. So we've got, this is our acid. This is our salt. Right. So we need to work out their content. They've mixed them together. They've done a dilution first, folks. They've done a dilution first. So let's do the salt first, because the salt is SO4 2 minus, and this is HSO4 minus. So let's do the salt first. So the SO4 2 minus was 25 centimeters cubed of 0.15 moles per dm cubed. You're not allowed to actually do that in your exam, by the way. Do be careful. I shouldn't do it really at all. It's bad practice. Shouldn't even show it to you. So I'm now going to do a dilution because it's going to be mixed together with another 75. It's going to take it to 100. So C1V1 equals C2V2. It's a dilution because the acid won't play with the base. Yeah, even though in this case I believe it would, but we're ignoring it. So the concentration, the original concentration is 0.15. The original volume was 25. The new concentration is a question mark times by the new volume of 100 because they added 75 and 25 together. The total is 100. Reorganize it over 100. Answer 0.15 times 25 divided by 100, and I get 0.0375 moles per dm cubed. Right, next. Now I need to do the HSO4 minus. The original was 75. Let's just run it straight into C1V1. So the original concentration, is it the same? Nope, was 0.1. The original concentration is 0.1 times by the original volume of 75, all over the new total volume of 100. 0.1 times 75 all over 100 gives me 0.075 moles per dm cubed. Now I can put those straight into my equation. The salt, which is 0.0375 over the bottom one of 0.075. Right. So now I just run those, rearrange it. They've given me the Ka, 0.012. Rearrange it, bring the acid over, 0.075. Bring the acid over. Yeah, bring the salt down, all over 0.0375. Get rid of my arrows. That's going to now give me H plus. Yeah, so 0.075 multiplied by 0.012 equals, divided by 0.0375 equals, there's my H plus. So H plus concentration equals 0.024 moles per dm cubed. Now just minus log it, minus log answer. minus log. Answer gives me a pH of 1.62. That is very, very, very acidic. That's a terrible buffer. Stupid. So annoying. Garbage. Skeletal formula of menthone. Ugh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. H18. Ethanol reacts with hydrogen cyanide in the presence of cyanide ions. Draw the mechanism. Right. Aldehyde. This is nucleophilic addition. Na. Polar. Right. Cyanide ion. There we go. Next picture. Now, because it's HCN, we need to show the HCN because it's a weak acid. And that's polar. And that breaks off that way. And I'm done. 4 marks. Take it. Next. A carbonyl compound F has the molecular formula C6H12O, reacts with iodine in an alkali solution. So this is the iodoform test. Give the formula of the group, give the name or formula of the group. You have to have that. I'm drawing it out. I'll also write it. Needs to have that group there. So either draw the picture or write the formula, either one. Name or formula. Yeah, that is a structural formula. It hasn't actually said. I'll do that one. Now, the problem is, of course, you need to have that kind of line here suggesting the bond. This is why I don't really like the formula bit. It's not a minus, it's a bond. It's the next part of the structure. Because the iodoform test, the iodoform test attacks the end, it attacks this guy here. Draw the skeletal formula of 4 possible structures of the carbonyl. 1, 2, 3, 4, 5, 6. Ketone, got to be that. So I've got hexane 2-one. All H's in the exam. You have to. You can't cheat. I'm doing it like you are. I won't cheat either. Next, add a branch. We've got to keep the same structure. We can't edit this end because we need that ending. Otherwise, the iodoform won't pick it up. So now I'm going to add on a branch just to make the carbons add up. You've got to do it. You have no choice. In reality, don't think it's saving you any time. It's not really. It's all of 10 seconds. Add a second branch. Add a second branch. I don't think they'd actually care if I went outside the box like that, but there we go. One more to go. Oh, I could move him to another position. That's quite clever, that. Yeah, quite clever. 5 in a row. Double bondo there. Very clever. Could also be that guy. Awkward to draw. 2 minutes. Yeah. Next. Carbon 13 that has 4 peaks in it, and identify F by drawing its displayed formula. Justify your answer by labeling the carbon atoms in the group responsible for the 4 peaks. Carbon. So this one would be 1, 2, 3, 4, 5. Carbon 13. 6 peaks, no symmetry. Yeah, this one would be 1, 2, 3, 4, 5, 6 peaks, no symmetry. This one would be 1, 2, 3, 4, 5. That one has symmetry, got less. Next one, 1, 2, 3, and all of these make 4. So there's my answer. Yeah, symmetry. So drawing the displayed formula, switch back to red for me. I have no idea how long this has been going on for now. So funny, you kind of, when you're doing exam papers like this, you just kind of get lost in them. You kind of have to, it does want displayed, so you've got to take your time with it. Yeah. There we go. And then labeling the 4 carbons. So I'd go 1, 2, 3, 4, 4, and 4. By doing the exam. Moving on. 6 marks. How long has this been going now? 1 hour 15. Okay, less than I thought. How much more have we got on this paper? Probably quite a lot. I'm only just coming to the end of section B. Holy moly. Right. Explain in terms of all the intermolecular forces involved why butanal has a higher boiling point than pentane, but a lower boiling point than propanoic acid. Guys, this is straight out of AS Chemistry Unit 1. Like, straight out of it. This is just a bonding question from Unit 1. They're being a little bit synoptic. It's very interesting. Okay, so in terms of London dispersion forces, they all have LDFs. Now, they're going to have picked these people for a reason. So butanal, pentane, I don't even need to bother with that one. Pentane, C5H, double it and add 2. And then propanoic acid, they're going to have picked these guys for a reason. So butanal, 4 carbons, 12 times 4, plus 3, plus, I don't know, plus something. 8 hydrogens. Yeah, 8 hydrogens, I don't know. Plus 8 plus 16. MR of butanal is 72. Yeah. No, it's not. I've written in the wrong one. 62. My bad. That's an MR of 62. Pentane, 12 times 5 plus 12 is 72. I just made a mistake there. 12 times 4 plus 8 plus 16. Really not doing that. Has an MR of 72. I'm an idiot. Pentane, 12 times 5 plus 10, plus 12 gives me 72. That makes sense. Propanoic acid, 12 times 3 plus 16 times 2 plus 6, 74. Right. So they've picked those because they've got very similar MRs. So the first bullet point I'm going to make is all have London dispersion forces that are similar since they have a very similar number of electrons. Similar number, shouldn't do that. Similar number of electrons. I'm actually going to, at that point, give the MRs. Oh, I've hit that with my hand. Nope, changed my mind, can't be bothered. So if they've got all have London dispersion forces that are similar, okay. However, next bullet point, butanal, however, has dipole interactions. Have dipole, thank you. Dipole attractions attractions as well. Next, this means as well, so butanal is higher melting point, higher boiling point, a higher boiling point than pentane. Yeah. Since pentane only has London dispersion forces. Butanoic acid has hydrogen bonding. Between the molecules. And it dimerizes the molecules. These are stronger than dipole-dipole. So much writing. Attractions. So higher boiling point than butanal. I'm done. Only 4 bullet points. I don't really care. I'm losing my patience with it. I attempted just to give the MRs. They'd probably mark the bits up there that I've done. I should give the order. So boiling point order is propanoic acid is greater than butanal, and butanal is greater than pentane. Done. Okay, on to section C. Right. Go away, will you? Entropy, it's giving us data. Right. First equation, delta S system equals sum of delta S super products minus sum of delta S reactants. Next, entropy of the surroundings equals minus delta H over T. Next, delta S total is equal to delta S system plus delta S, delta S surroundings. Right, let's run them through. So first thing, they've given an equation with the delta H. Work out the system first. Delta S cis. So, and that is products minus reactions because it's super. So the products are here. So that is 2 times KBr, which is 2 times 95.9. Yeah. This I'm working out delta S products. Let's do delta S P first. Yeah, so 2 times that plus 3 times oxygen. 3 times 205.0. Give me a total. So 2 times 95.9 equals plus brackets 3 times 205.0 equals total 806.8 for the products, right? Delta SR. So this is the reactants, which is simply 2 times 149.2, and we're done. 2 times 149.2 gives me a total of plus 298.4. Right, so delta S of the system, delta S cis equals products minus reactants. Type it in, open brackets, plus 806, so easy, 6.8, close brackets, minus brackets, plus 298.4, close brackets. I get a delta S system equaling plus 508.4. Don't forget to add your plus. Right, next, we've now got the delta H and the temperature. There's the delta H and there's the temperature. So let's run that one. Delta S surroundings equals minus brackets, don't forget to do that, minus 67.2, all over the temperature of 298 in Kelvin. So this is minus brackets, minus, easy to forget, there we go, minus 67.2, close brackets, divided by 298, equals, makes it a plus 0.226. The units, by the way, do be careful. The units are joules per Kelvin per mole. Joules per Kelvin per mole. Now this one's awkward because this is now kilojoules. Yeah, kilojoules per mole per Kelvin. Yeah, that's the problem with the surroundings because we're using the kilojoules per mole as the delta H. You've got to watch out for that. Now, to work out the enthalpy change of the S total, you've got to remember to convert all of them. Now, S tends to be in joules, so I prefer to make everything into joules. So I'm just going to times that by 1,000 to get me 200 and times by 1,000. Gets me 226.5 technically if I have the 5 in there. No. See, that's 5. So that becomes much larger. Joules per mole per Kelvin. Doesn't really matter which order I put those in because they change all the time. Right, so add them together. Plus 508.4 plus, put them all in a bracket, plus 226.5. It's not 0.5, it's 0.0 because it's rounded it up. Yeah. So brackets plus 508.4, close brackets, plus 226.0. And I get a S total of plus 734.4 joules per Kelvin per mole, and I'm done. Which seems very reasonable. We're going from a solid to a whole load of gases. It's very exothermic. It's all good. Yeah, works. Oh, determine the order. It's a half-life graph. Time at the bottom, concentration. Determine the order showing on the graph. So it's a half-life graph. So half-life is when it starts at the concentration of 1, halve it. Yeah, next, halve 5, 2.5. Now this is 1, 2, 3, 2.5 is here. It's first order. Yeah, even do a next one if we. The screen's cut off because it sucks. Cables, cheap cables. Sorry, my laptop's having a quick freak out. Let's move that back over there. There we go. So the answer is first order. First order. Do I actually need, because half-life 1. Half-life 1 equals 200 seconds. Half-life 2 equals 200 seconds. Same half-life. They're the same, so it must be first order. Next. The initial concentration of bromate ions, determine the order with respect to bromate and H+. Okay, so this is a nice easy bit of stepping. Times by 2. Times by 2. This is easy. Bromate, BrO3 minus, is first order. Next, H+. So in this case, we've got to do some stepping. Oh, no. Yeah, let's do an easy stepper though. Yeah, so this one's times by 3, which means according to the bromate, we would have gone up by times by 3. So 3.6 exponential minus 3 times by 3. Yes, that will take me to 0.0108. Now I'm going to go from there to there. So 4.3 exponential minus 2 divided by answer. The answer is 3.9. That's times by 4. So that's times by 4. And they doubled it. They doubled it, and it went up by 4. So H plus is second order. Do I need to? You must explain your working. Okay. All right. Okay. Must explain your working. When comparing run 1 and 2, bromate was doubled. H plus kept same. Rate doubled. Yep, rate doubled. Next, that explains the bromate. Next, comparing run 1 and 3, when H plus concentration doubled, rate quadrupled. Rate went up by times 4. Done. Give the overall rate equation. Rate equals K bromate to the power 1 and H plus to the power 2. Include units for the rate constant. Units for the rate constant. So we know that the rate is moles per dm cubed per second. It's always the case. So if I rearrange it, that one will cancel with the moles per dm cubed, but those squared ones won't. Then we've got to, okay, I'll explain this properly. Explain this properly, guys, for those people who don't know how to do it. Hi, Dixon, thanks for coming. So the rate is moles per dm cubed per second. And K then is a question mark, but we then have bromate, which is moles per dm cubed. Yeah. And we've also got H plus, which is moles per dm cubed squared. If I reorganize that, that becomes moles per dm cubed per second over moles per dm cubed of the bromate. Yeah, BrO4 minus, multiplied by moles per dm cubed squared by the H plus. That's the same as just writing it twice. I prefer to write it twice. Yeah, so I get that cancels with that. These two now combine to give me moles to the dm to the minus 6. Now I need to bring them up. So that becomes, the final answer will be moles to the minus 2, dm to the plus 6, s to the minus 1. Okay. Next, plotograph. I hate you. I hate you. I hate you. I hate you. I hate these graphs. They're hard. And then use it to determine the activity. 7 marks. How am I doing on this? 1 hour 35. How far away am I from? I'm on the last question. Okay. At least I'm on the last question, folks. And I'm still within the allotted time. I'm surprised considering the level of teaching I've been doing. But I haven't done enough. I didn't want this to go on forever. Right. This is a nightmare for me, guys, because you're lucky. What I'm going to do is I'm going to bring my graph paper up to here like you would. There we go. That makes things a little bit easier for me. Just a little bit. Okay. So let's plot our graph. I'm going to switch to a black pen, which is a bit... No, I'm going to stick to a red pen, actually. I don't mind the red pen. So the first thing is, what I'm probably going to do is just draw some axis on here. I always think use all the paper. You just draw your lines originally. Yeah, there's my 2 lines. Pen's not thick enough. Should have made my pen thicker. There we go. Get rid of those. Right. Next thing is my numbers. So Steve against Sarah. So we've got Steve, plot a graph of LNK against Steve. So that's LNK. So on this, I'm going to write LNK, which there are no units. Fine. But the problem is that it's negative. I'm going to move the LNK a little bit further off to one side, by the way. LNK. So the biggest number there is minus 4.93. The biggest number. Yeah, I've suddenly realized the graph's upside down. It's a negative graph, isn't it? Sucks. Students are going to ask, how did you know it was a negative graph? Because it's going down. Yeah, we're going from minus 10, yeah, minus 10 to minus 4. So this is going to be, it's getting more negative. This is going to be minus 4. And this one's going to be minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 11. Fits beautifully. Yeah, that's literally all I'm going to do for that axis. What a nightmare. Next. Oh, look at these. Right, first of all, get rid of the 10 to the minus 3s. So I'm going to put over here 1 over T, 1 over T, which the units are, and the units are per Kelvin. I'm also going to write, oh, the problem is I'm running out to say, wait, I'm going to now put this over here, 1 over T, 1 over T per Kelvin times 10 to the minus 3. So what I'm going to do, I'm happy to see you, Mr. Duncan. Oh, Zakaria, it's so nice to see you too. Nice to see you too. Thanks for coming. Right, let's figure out my bloody numbers. So I've got rid of my 10 to the minus 3s. So I'm going from 3.3 to 3. What a nightmare. So you don't do any of those zigzaggy lines thingies. My smallest one is 2.9. Yeah, so this one here is going to be 2.9. And then the biggest one, so then let's go to 3, then 3.1, 3.2, 3.3, and 3.4. Fits beautifully. They've done that on purpose. That's rather nice. They've been really generous. Right. Now I can plot my graphs. Okay. So 3.3, which is over here. 3.333333, which is a flipping nightmare. Which is a third of the way along. Third of the way along. 10, about there. 3.33 is minus 10.2. Ruler. Minus 10.2, which is, since that's in the middle, is there. It's there. There's my first plot. There we go. Next. It's actually a nightmare, this. So I've ticked him off. Next, 3.23. Oh my God. 3.23, which is not there. You evil thing. Get rid of my ruler. 3.23 is there. Right, where's that one going? No, 8.92. 8.92, which is going to be there. There we go. Next, take him off. 3.13. 3.13 minus 7.51. 7.51. There we go. Next, 0.3 and minus 6.21. That's awkward, isn't it? Slides. 6.21. 6.1, 6.2. There, give or take. There we go. And then 0.93. This is grim. 0.93 at minus 4.93. 4.93 is about there. Oh, that's wrong. Made a mistake. I can see the bump. That's 6.5, not 6.2. Because it's 5 squares. Ah, 6.21. There we go. Is that a straight line? It is indeed a straight line. Wowza. Yeah, okay. Cool. There's my graph. Grim. Right, now that I've done the graph, what I now need to do is work out its gradient to work out the activation energy. This is my last question, right? Yes, end of paper, total for paper. I'm past the line though. I'm past the time, aren't I? No, I've technically got 4 minutes left. So let's work out. So we know whenever we get this is y equals mx plus c, and m is the gradient. So the gradient of this line, gradient equals minus EA over R. So what we need to do is, and also, of course, it also equals the gradient also equals delta y over delta x. Yeah, so gradient is always delta y over delta. I always teach that in my lessons as boys on top of girls, because boys have got a Y chromosome and girls have got an X chromosome. Easy to remember. Yeah, I'll get rid of that now. Lol. Kids never forget it. This thing is very entertaining. So what we now need to work as the gradient. So we need my change in Y. So we're just going to go as big as possible. I'm going to extend that line. I'm going to extend that line as long as I can. Just make it all the way down. It makes it easier to read the graph, because what that means is no matter what I do, yeah, so I can go, I'm going to read the graph from here. Here's my delta x all the way until the end of the page. Or is it? No, it's not quite, because the line's not on the page. That's irritating. Have to read just up to it. So up to there. Right. They won't care. It won't matter really. It's tricky that though. If you want to try and make it easier for yourself, I'm happy to try an alternative method since it's going off the page down there. Let's try an alternative. Let's just pick nice easy numbers. Yeah. Let's make one of these easy. Yeah. Let's make the delta y. We're going to start at 10. Yeah, we're going to start the delta. We're going to make the delta y equal a value to make it easier for ourselves. So that way, at least only one of them is going to be tricky. Yeah, I'm going to go at 10, and I'm going to go up to 5. There's my delta y. That's my delta y. Yeah, and it's dead easy. It's just going to be minus 5. Minus 5. Yeah, because I'm going from minus 5 to minus 10. So it's negative 5 because we're always coming down. Yeah. Next, I now need to figure out where these points are. Yeah, let's get rid of him. Oh, nuts, put that back. Get rid of him, though. And then get my ruler And I now need to measure what this delta X is. Yeah, it should be a bit higher than that, but it's fine. So that one is going to be 29. Yeah, I shouldn't really need those dashes anymore, do I? Okay, going to confuse me. So this is going to be 29.12345. So my delta x equals 2.9 times 10 to the minus 3, 2.945 minus, going to go all the way over to this one, which is going to be minus 3.320, I believe. Yep. Right, I can now work out that value. So it's getting bigger. Yeah, so in fact, I've done it the wrong way around. It's going to look like it's going negative, but it's not. So I'm actually going to reverse that. 3.320 minus 2.945. So my difference, my delta x, in reality, I want to reverse. Oh, yeah, times 10 to the minus 5. That actually works because they're both times 10 to the minus 3. 10 to the minus 3. I'm going to reverse those because it is getting larger. So I'm just going to move these around so you know that I'm not getting a bizarre answer for a calculation I didn't do properly. Okay, times 10 to the minus 3. There you go. So that now equals 0.375 times 10 to the minus 3, I believe. Let's run it through. 3.320 exponential minus 3 minus 2.945 exponential minus 3 gives me 3.75 times 10 to the minus 4. I'm completely off. Just ignore me. Calculator's gone. Something on it. 75 times 10 to the minus 4. Thank you, Mr. Duncan, for checking, idiot. So that's my delta x. Now I just need to insert these into my equation. So the gradient equals, got to keep everything on my screen, my delta y, which is minus 5 over 3.75 times 10 to the minus 4, my change in x. So minus 5, now it is positive, yeah, minus 5 divided by answer, which is on my calculator, equals, I get a gradient is minus 13.333. So there's my gradient. Now that's a good thing because it means that I'm going to get a positive energy change. Because what I'm now going to do is I'm going to reorganize this equation, bring R over here. So R multiplied by my gradient, will give me minus EA. Oh, hang on a minute. No. First of all, flip the sign, Mr. Duncan. Flip the signs, make the gradient negative. Yeah, so the gradient becomes a negative gradient. Yeah, that becomes minus the gradient. Yeah, and then equals EA. Yeah, now what I can do is input my numbers, which is 8.31 multiplied by minus brackets minus 13.3, and it'll flip it into a positive energy. So 8.31 multiplied by minus brackets minus 13.3 close brackets, and I get an activation energy of plus 110.5 kilojoules per mole, and I'm done. Wowza. Blimey, what a mess. Right, guys, let's mark it. Ugh, that was an awful long paper. I'm off my time. Still overshot, probably. Yeah, overshot. The graph took me over 8 minutes. Nightmare. Anyway, back to the start. Let's mark it. Need to find my mark scheme now. There you go. Let's mark it. Okay. Ugh. It's in my throat. Carbon dioxide is the highest molar NP. Good. P and Q. Yes, absolutely right. A, there we go. C is not correct. Bromine standard state is a liquid. I like it. Next, 4 is C. 4B is B. Oh, darn it. First mistake. Yeah, first mistake. The answer, of course, is magnesium. I didn't consider the size, did I? I was too busy trying to explain it. Yeah, so calcium is larger than the magnesium 2+. So quickly to show you. So magnesium is a tiny 2+. Calcium is the bigger 2+. So the magnesium has got much more distortion than magnesium has much more distortion than calcium does. First mistake, didn't consider the size of the 2+ cations. My bad. Oh, well, it's never perfect, is it? All I can do is do my best. I would never expect to get them all right. It's hard, this. It's not for everybody. So, 4A is C. 4B is B, yes. 5, C. Thank you. Okay. Next. Number 6 is A. Number 7 is A. Number 8 is C. Number 9 is B. 9A is B. 9B is C. 10A is U. 10B, this was, I struggled with this one, methyl red. Found that one horrible. Took too much time. B, yeah, sorry, 10C is B. Phew. Whew. Question 11 is B. Question 12 is C. Question 13 is D. Question 14 is C. Question 15 is C. Question 16 is D. And we're done. Okay, on to the long answer. Long answer. 17A, lactic acid molecule have a chiral carbon. That is a non-superimposable on its mirror image. Allow, there are 4 different groups. Allow, it is chiral. Allow has a chiral center. Allow has a chiral carbon. Done. The sample is racemic mixture. Now going to form, yeah, my enoic acid. I like it. Identify, it's going to be butan 1-ol is X. Y is PCl5. And Z is the N-substituted amide. Like it. Correct number of carbons too? Yeah. Next. Ethane 1,2-diol. That was a weird diene. Sorry, weird dioic. That was weird, that. C5, I hated that question. Wasn't even worth the 1 mark. I would have bailed in the real exam. Not a carboxylic acid. It is an ester. Yeah. Structure E. Structure E is there. I like it. Labeled people. A, B, C, D. Yeah, fine. Yeah, all labeled. No effect on KP. Forward reaction is exothermic. 2 marks. Yield decreases. Yield will also decrease. KP will decrease because the forward reaction is exothermic. I like it. KP equation. Oh, did I ignore missing G's? Didn't include my gas symbols. It's close though. Close. Next, this was hard, the card calculation. But my final answer, 1/6. Did it say to give it to 1 decimal place? The appropriate number of significant figures. Penalize incorrect rounding once only. Allow answer from previous 2 or more significant figures. 35 atmospheres. I mean, I got the right number. Allow fractions. Correct answer to 2 or 3 significant figures with no working scores 4. Okay, I stuffed that up, didn't I? I'll give myself 3 since I should have given it to no more than 3 sig fig. I don't know why I went to 4 then. Don't know why. Fine. I got everything else. I'll give myself 3 and say 35. RTFQ. Appropriate number of significant figures. Didn't think about it. I did an unusual thing there. I never give it to 4 sig fig because I know just to give it to 3. Made a silly mistake there. Silly mistake. Next one. Sulfide. Yeah, okay. It's fine. No one. Yeah, okay. I can see that one in the mark scheme. Let's move the concentration of the sulfuric. And then the answer being 18. Did it ask me to give 3 sig fig again? Oh, 8, 9. 18.73. Yeah, 0.73. Okay, that's fine. Grim. Stupid question. Calculation of H plus. Yep. This question has annoyed me massively. Question has annoyed me. Hi, Sophia. This is the A2 paper, Sophia. You don't want to be here for this. I hated this equation. This question sucked. First equilibrium, the first ionization is complete since Kc is very large. Second is very small. Is that it? Allow second equilibrium shifts left. Stupid equation. Next, give the 2 equations for the reactions. I like it. Fine. I should have reversed that, flipped that over. Just in general, I would have got it, but it's not good chemistry. They would have been mean to me on that one, I reckon. 1.62. I like it. I hate these questions. They annoy me. Get half of them wrong half the time. 19A, C10, H18O. Nice, easy mechanism. Oh, do they need a product? And final. Did I forget to draw the final product? No, do not need. I shouldn't need the curly arrow on the lone pair on O and the curly arrow on H into anywhere on CN and final product. You don't need it. Thank you, Excel. Excuse me. Sorry, I didn't say that. Add on your final. That's garbage. That's complete garbage. It's not true. You do not need your final. Do you know what? Edexcel changed their minds. I literally hate them, you know. I hate them. They're just horrible example with inconsistencies. Drives me nuts. Absolutely crazy. Skeletals or normals? Yeah, it's all good. Yeah. With everything labeled, I like it. Oh, this one was horrible as well. Pentane only has London forces, also has permanent dipoles. Should I actually say that pentane just has London? Yeah, I definitely did. Propanoic hydrogen bonds. So I definitely get them for saying how butanol. I definitely get those 3. They're all similar strength since they have the same number of electrons. Yeah, so there's the MR bit. Yeah, there's the MR bit. Similar number of electrons. Yep. Strong dipoles are stronger than London. Hydrogen the bonds are stronger than. Yeah, that's absolutely fine. Stupid question. Right, let's keep going. System 508. Surroundings. Yeah. Final. I rounded something badly. Bear that in mind. Shouldn't have rounded it. Why? I don't know. I don't think they'd care, but I certainly wouldn't round it in future. Keep those numbers. Half-life 1 and 2. Sample of half-lives, fine. Do not award 0 a second yet standalone mark. I just don't understand why it doesn't say first. Why doesn't? Oh, it's over there. On first order. Respect 1 and 2, rates, triples and doubles, all that kind of garbage. Yeah, whatever. Oh, I didn't actually write down so second. I did originally, and then I do second order. So irritating. I then get it in the next question. So stupid. Oh, DM to the 9? Have I made a mistake? Oh no. What? Moles to the -3. Huh. What have I got done here? Oh, is there H plus in there too? Oh, what? Where's that come from? Whoa. Have I made a mistake? I definitely have made a mistake. The overall rate equation, including its units. And in large excess. Oh, totally stuffed that up. They're saying it's first order with respect to BR minus. The whole question links together. Oh, I got totally done on that. I did not get that correct. No and no. However, if I gave the incorrect previous answer, then gave the correct units from my rate equation, it would get error carried forward. But I'm not going to bother. I've totally stuffed up that part. Okay, guys, there you go. There's my error of the day. I didn't realize, I just assumed that this was a continuation of experiment 2, and I ignored experiment A. So I've really stuffed that up. What I should have realized was that the bromide ion is here as well. Yeah, the bromate ion, as well as the bromate ion, yeah, the 3 minus, as well as H plus, yeah, squared, H plus squared, there you go. So that's what I should realize I should have done. And then I would have got, yeah, three of the moles per dm's cubed. Oh, well. And then plot your graph and give me a gradient. Example of the gradient. Oh, have I stuffed that up as well? What have I done there? They've got Kelvin. My graph's good. My graph's good, but my gradient doesn't appear to be. Gradient. Oh, yeah. There you go. Minus 12.8. Yeah, sign and with the, do I need units? And units of gradient. I didn't give the units for the gradient, which is just, what would they be? Y has no units. Oh, it's per Kelvin. Yeah, because that would have been Kelvin to the -1. There's no units here, so you bring it up, it just becomes Kelvin. Huh. That's clever. So I'll lose 1 mark for that for sure. But my answer's, am I correct sign activation energy or calculation of activation energy, expected range. There you go. I'm within the expected range, which is fine with the correct units, which I did. So I definitely only got 6 on that last one because I didn't give the units for the gradient. But hard paper. They always are, guys. Right, I'm going to end the webinar there. It's been going a long time, 2 hours, 4 minutes. I'm going to end the webinar there, guys. I hope you found it useful. they're always tough, the A2 papers, no matter how you take them. They're tough on time. Yeah, you've just got to keep practicing and try and keep a level head. It's the best thing you can do. Just be calm, think it through. Just remember, once you're into the paper, it'll just flow. You'll just be like, okay, I'm doing this. You won't be worrying about the time. Just try to relax. Take your time, read the questions. If you're not 100% sure, take a break from it. Go to the next question. Yeah, and come back to it. Just don't forget to go back to it. I'll see you guys all later for